Now I want to take a look at finding center of mass in 3 dimensions. In 3 dimensions, the density function will have 3 coordinates. So my rho will be given in terms of x, y, or z, and it will be defined over a closed region D in R3 space. In 3 dimensions, my density will have units of mass per unit volume, such as kilograms per meter cubed. The center of mass in 3 dimensions depends on the mass of the region, which is the integral of the density function over D. We now have 3 moments to deal with. We will have m sub yz, m sub xz, and m sub xy. These all represent distances from the yz plane, the xz plane, and the xy plane respectively. M sub yz will have an x in the integrand, m sub xz will have a y in the integrand, and m sub xy will have a z in the integrand. If you get confused, simply look at the subscript. The variable that's missing in the subscript is the variable that you're going to incorporate into your integrand for your moment computations. The center of mass in 3 dimensions will now be located at a point x bar, y bar, z bar, where x bar is equal to capital M sub yz over little m, y bar is capital M sub xz over little m, and z bar is equal to m sub xy over little m. The mass of a 3-dimensional object is the integral of the density function over d, so that m is equal to the triple integral over d of rho of xyz dv. We can also express our region in cylindrical or spherical coordinates, and everything will work the same, with the exception that we have to pay attention to what happens with my dv differential when I switch between coordinate systems. If I let rho be an integrable volume density function defined on a closed bounded region D in R3, the coordinates of the center of mass of the region will be given by x bar is equal to capital M sub yz over little m, which is equal to 1 over little m times the triple integral over the region D of x times rho of xyz dv. Y bar is equal to capital M sub xz over little m. This is given by 1 over little m times the triple integral over the region D of y times rho of xyz dv. And z bar is equal to capital M sub xy over little m, which is equal to 1 over little m times the triple integral over the region D of z times rho of xyz dv. This is all where little m represents the total mass, and capital M sub yz, capital M sub xz, and capital M sub xy are the moments with respect to the coordinate planes. We always want to look for opportunities to make our life easier, and as I increase the number of integrals I have to compute, this becomes much more important. So I'm going to look for ways to use symmetry or geometric relationships that I already know, and that's when density is a constant, or I want to be able to convert to a different coordinate system in order to make my integrals simpler. Here's an example. I want to find the center of mass for the solid region bounded by the cone z is equal to 16 minus r and the plane z is equal to 0. We're going to assume here that my density is constant. And since my density is constant, I can assume that it's 1. This means that our mass is given by the volume of the cone. I'm going to use a geometric formula for the volume of the cone to make this easier. My volume of a right circular cone is given by 1/3 pi r squared h, where r is the radius and h is the height of my cone. In this case, my radius is 16 and my height is also 16. My volume with a constant density will give me my mass, which will be equal to 1/3 pi times 16 squared times 16. This is equal to 4096 pi over 3. This is my total mass. Now I'm going to look for some opportunities to perhaps use symmetry. The cone is centered on the z-axis. This means that it will be symmetric about both the x and y axes. This tells me that x bar is equal to y bar is equal to 0, so that all I have to do here is compute z bar. Z bar is equal to 3 over 4096 times pi times the integral from 0 to 16 of the integral from 0 to 16 minus r of the integral from 0 to 2 pi of rz d theta dz dr. I integrate the innermost integral and I'm left with 3 over 4096 times pi times the integral from 0 to 16 of the integral from 0 to 16 minus r of 2 pi rz dz dr. Now I compute the middle integral. I get 3 over 4096 pi times the integral from 0 to 16 of pi r times 16 minus r quantity squared dz. I have one final integral to compute. I do that integration term by term, and I get 3 over 4096 pi times the quantity 128 pi r squared minus 32 thirds times pi r cubed plus pi over 4 times r to the fourth evaluated from 0 to 16. I plug in the limits of integration and simplify, and I get 4. This tells me that the coordinates for my center of mass, x bar, y bar, z bar, is located at 0, 0, 4. Let's work another example. I want to find the coordinates of the center of mass for the interior of a cube in the first octant that is formed by the planes x is equal to 1, y is equal to 1, and z is equal to 1, with rho of xyz equal to 2 plus x plus y plus z. My total mass is given by the triple integral over the region D of rho of xyz dv. This gives me the integral from 0 to 1 of the integral from 0 to 1 of the integral from 0 to 1 of the quantity 2 plus x plus y plus z dx dy dz. I compute the innermost integral with respect to x first, and I'm left with the integral from 0 to 1 of the integral from 0 to 1 of the quantity 5 halves plus y plus z dy dz. I compute the middle integral. I get the integral from 0 to 1 of 3 plus z dz, which is equal to 7 halves. Now I want to examine the region itself and determine if there's some kind of symmetry either in the region or in the density function that I can take advantage of. I notice that both my region and my density function are symmetric about the line x is equal to y is equal to z. This means that x bar is equal to y bar is equal to z bar. I only need to find one coordinate in order to have them all. See how much work we're saving by just simply thinking about this for a few minutes first? So I'm going to compute x bar. X bar is equal to 2 over 7 times the integral from 0 to 1 of the integral from 0 to 1 of the integral from 0 to 1 of x times the quantity 2 plus x plus y plus z dx dy dz. I work from the inside out. This gives me 2/7 times the integral from 0 to 1 of the integral from 0 to 1 of the quantity 4 thirds plus y halves plus z halves dy dz. I compute the middle integral, and I get 2/7 times the integral from 0 to 1 of 19 over 12 plus z over 2 dz. This gives me 11 over 21. My coordinates for my center of mass, x bar, y bar, z bar, will be given by 11/21, 11/21, and 11/21. Now you get to try it. Pause the video and find the coordinates of the center of mass of the solid in the region bounded by the paraboloid z is equal to 4 minus x squared minus y squared and z is equal to 0, with a variable density of rho of xyz is equal to 5 minus z. When you are ready, restart the video to check your understanding. Just like before, I want to examine ways I can make my life easier. First, I need to find the mass, but it will simplify things quite a bit if I convert to cylindrical coordinates first. If z is equal to 4 minus x squared minus y squared in rectangular coordinates, in cylindrical coordinates z is equal to 4 minus r squared. With this conversion, my limits of integration on z will go from 0 to 4. We also get limits of integration for r, which will go from 0 to the square root of 4 minus z. And my limits of integration for theta will go from 0 to 2 pi. So now I'm going to compute my mass. My mass, little m, is equal to the integral from 0 to 4 of the integral from 0 to the square root of 4 minus z of the integral from 0 to 2 pi of r times 5 minus z d theta dr dz. I compute the innermost integral. I'm left with the integral from 0 to 4 of the integral from 0 to the square root of 4 minus z of 2 pi r times the quantity 5 minus z dr dz. I finally compute the outer integral, the integral from 0 to 4 of pi times the quantity z squared minus 9z plus 20 dz. This gives me 88 pi over 3. You'll notice I chose to integrate with respect to theta first. This allowed me to eliminate one variable from that integration piece right away. So notice that I am picking an order of integration that helps simplify what I'm integrating each time. Now that I know my mass, I want to examine the region and density function to see if there's anything I can take advantage of to make my life simpler. I'm going to notice that the density only depends on z. With that in mind, I'm going to know that x bar and y bar will both be equal to 0. I only need to compute z bar. How about that for reducing my workload? Z bar is equal to 3 over 88 pi times the integral from 0 to 4 of the integral from 0 to 2 pi of the integral from 0 to the square root of 4 minus z of z times r times the quantity 5 minus z dr d theta dz. I again pick my order of integration in a way to help me eliminate variables one at a time and simplify my process. I get 1 over 176 pi times the integral from 0 to 4 of the integral from 0 to 2 pi of the quantity z cubed minus 9z squared plus 20z d theta dz. I integrate that middle integral and I'm left with 3 over 88 times the integral from 0 to 4 of the quantity z cubed minus 9z squared plus 20z dz, which gives me 12 over 11. My coordinates for my center of mass, x bar, y bar, z bar, is given by 0, 0, and 12/11. This is how I can compute the center of mass in triple integrals. Triple integrals can get quite complicated, so always take a few minutes to look for ways that you can take advantage of symmetry or use alternate systems of coordinates to make your life easier. Be sure and let me know if you have any questions.